Okay, so you might want to pause the video. Obviously, I drew the circuit before I started recording here, so you can catch up and record this. But just to see here, we have a differential op amp here, 10 volt minus 10 volt power supply, 1 milliamp biasing current here. Which again, remember this is being set up by a current mirror, 10 kilo ohm RCs, VB1, VB2. So let's see what the problem is going to be here. Well, first off, the problem tells us that beta is equal to 200, that VBE on is equal to 0.7 volts, VA is equal to infinity, and we're supposed to find VE, VC1, VC2 for V1, B1 equals VB2 equals 0, positive 5, and negative 5 volts. So we're going to do it for all three cases here. So first off, this is very important here. What voltage mode are we in? Since VB1 equals VB2, we are in common mode voltage, which is good for us because it makes some of the things a little bit easier. For instance, we know that we can figure out what IC is, and we can figure out VC1 and VC2 pretty quickly here. And so we'll see how we can do that here. So first off, actually we can figure out VBE and VE as well pretty easily. I'm just getting myself a little sidetracked here, but we can do all of these pretty straightforward, pretty easy. Okay, so let's first look at, we're looking for VE. And I'm going to just do VE for all three cases. Well, VE is this voltage right here. And then I also know here, this is VB. And because they're tied together in common mode, that's also VB. And we also know that VBE on is 0.7, and since these are in forward active mode, that this would be VB minus VE. So we know that for, we'll just say here A, VB equals 0 volts, you have 0.7 is equal to 0 minus VE, which gives us VE equals negative 0.7 volts. If part B, if VB is 5 volts, we have 0.7 is equal to 5 minus VE, which would give me that VE is equal to, well, assuming that I can do basic arithmetic right now, that would be 4.3 volts. In part C, if VB is negative 5 volts, we'd get 0.7 is equal to negative 5 minus VE, and VE would be negative 5.7 volts. Now, the only other thing we have to find is VC1 and VC2. Now, because this is in common mode voltage, we know that VC1 is going to be the same thing as VC2 because we're in common mode voltage. And so to get that, we would simply do the 10 minus the current coming through here, and we'll call this current IC. It's also the same current is going down through there because we're in the common mode. And remember here that IC is basically just IQ over 2, which would be 1 milliamp over 2, 0.5 milliamps. So VC1 is going to be 10 minus 0.5 milliamps times RC, which is what, 10 kilo ohms. Which would get me 5 volts. Now this is what VCE is. Now that's, VC1. So this is at positive 5 volts, and this is at positive 5 volts. Now it turns out you can change the base voltage to whatever you want to, and that's not going to change because my biasing current is 1 milliamp. So I got 1 milliamp still coming down through here because I'm in common mode. But the thing that will change here, and we can look at it here, is, well, VC1, so for A, B, and C, VC1 is 5 volts. Now I know the problem didn't ask for this, but we can see that VCE changes for each one. So for part A, VCE would be 5 minus negative 0.7, 5.7 volts. B, VCE would be 5 minus 4.3, which is 0.7 volts. And then for part C, we'd have VCE is equal to 5 minus negative 5.7 volts, which would be 10.7 volts. And one of the reasons some of these things would be interesting for you is if you're talking about VCE, that's, you're talking about the power being, well, a majority of the power that's being dissipated by the transistor. And so, depending on what the input voltage is, that transistor is going to be dissipating more power. Notice that if the input is 0, that we're dissipating 5.7, well, there's a voltage drop of 5.7 volts, so we would be doing 0.5 times that, which math right now, what would that be? Gosh, can't think of it right now. Let me pull my calculator up here. This is pathetic. 5.7 times 0.5, so 2.85 milliwatts if there's 0 volts in the common mode. But then if you have 10.7 times 0.5, well, that would be 5.35 milliwatts. And that's important because when you're talking about a data sheet, there's what are considered maximum ratings, but you really don't want to be running at maximum ratings. Those are, what it can absolutely handle. And so if we're just thinking about what kind of power these transistors would need to be able to dissipate, or what kind of heat sinks we might need to apply. Now, it turns out that in milliwatts here, we're not talking about that much power, but it does, come into play. And some of you, I'm sure, have seen it where, you put on a chip and it can, sometimes those ICs can heat up pretty good, and, sometimes you have to heat sink them because of that. Alright, but this is going to kind of wrap up this example here. We're next going to move into some actually, some of the DC transfer characteristics, and looking at the transconductance, and then we'll get into the small signal analysis. How do we analyze this with a small signal to actually get the gain?